Hello, welcome to Shivan Solution. Today in this video we will discuss 2020 JAM Chemistry second part, that is question from 11 to 20. Okay, let's start. Question number 11. At constant pressure, the mu T diagram for pure substance that sublimes is. Okay, let's see how to solve this question. To solve this question, we should know the relation between mu, that is chemical potential, T temperature, and S entropy. So what is the relation between these three? The relation is dou mu divided by dou T equal to minus S. This is the relation between chemical potential, temperature, and entropy. Okay. So if we plot a graph like this, temperature versus mu, okay, how the slope of the entropy will be? The slope of the entropy must be negative. That means it should be like this. Okay, so the slope should be negative, so the nature of the graph should be like this. So if you look at the options, you can see option B and option D have positive slope for sublimation. So that means we should look for the graph of gases. If you look at the graph of gases, you can see the slope of the gas plot is positive for option B and D. So we can eliminate that two options. Now just look at the option A and C. Let's discuss about the question. Options A and C. Okay, so these are the options given, A and C. If you look at the option A, you can see from here to here temperature increases. So this point will be, this is solid to liquid conversion, so it will be a melting point. This is solid to gas conversion, this is boiling point, this is sublimation point. Sublimation point. Okay, so this is the sublimation point, this is the melting point. Okay, normally what happened is, when we heat a solid, first it will convert it to liquid and then it converted to gas. So that is the usual procedure. But during sublimation, what happened? During sublimation, without going into liquid, a solid directly converted to gas. That transformation is known as sublimation. So that means before reaching the melting point, it will reach the sublimation point. Here you can see, if you look at the temperature, this is at lower temperature, so first it melts, then only the sublimation takes place. But here if you look at the graph here, this is the melting point. Okay, this is the sublimation point. Okay, so you can see it here, sublimation reaches before melting point. So this is the correct sublimation graph. Okay, so in this particular case, this is at lower temperature, sublimes before melting. So this is the graph which represents the sublimation. So the answer is option C. Question number 12. The force constant for HCl and DCl are the same and both can be considered as harmonic oscillators. HCl has a fundamental vibration transition at 2886 cm inverse. The ratio of 0 point energy of HCl to DCl is. To solve this question, we should know the equation for energy of harmonic oscillator. Okay, energy of harmonic oscillator epsilon is given by nu plus half omega bar oscillation. Okay, this is the energy of simple harmonic oscillator. Okay, so what is 0 point energy? 0 point energy means at the lowest energy, the energy when nu equal to 0. Okay, so when nu equal to 0, it will become energy will become half omega bar oscillation. This is 0 point energy. Okay, so we should compare the 0 point energy of HCl and DCl. So let's represent half omega HCl divided by half omega DCl. So this is what we should find out. So it will be cancelled out. So ultimately we should find omega bar HCl divided by omega bar DCl. Okay. So to solve this question, we should know the value of omega bar oscillator. Okay. So that means frequency of oscillation. So what is the frequency of oscillation? What is the relation between frequency of oscillation? Omega bar oscillation for a harmonic oscillator will be equal to 1 by 2 pi c into root of k by mu. Okay, this is the equation for omega bar oscillation. So what are the constant? Pi is the constant, normal constant 3.14. C is the velocity of light. K force constant. Mu reduced mass. Okay. So in the question itself, you can see the K for HCl and DCl are same. It is already given in the question. So K is same for HCl and DCl. That's already given. So what is the value of mu? Mu is given by mu equal to m1 m2 divided by m1 plus m2. m1 and m2 are the mass of each atom. For HCl, mass of hydrogen and mass of chlorine, that is m1 and m2. For DCl, it will be mass of deuterium and mass of chlorine. Okay. So now we should find out the omega bar oscillation of HCl divided by omega bar oscillation of DCl. So what is this? From this equation you can say omega bar oscillation of HCl divided by omega bar oscillation of DCl will be equal to 1 by 2 pi c into root of k by mu HCl divided by 1 by 2 pi c into root of k by mu DCl. Okay. So it will be cancelled out. You can see it here. So this will be cancelled out. It will be equal to root of mu DCl divided by mu HCl. Ready? Now we should find out the value of mu DCl. Mu DCl will be equal to mass of m1 m2. m1 means mass of deuterium 2 into 35 divided by 2 plus 35. Okay. It is nearly equal to 2. It is nearly equal to 2. And mass of mu HCl, what is mu HCl? Mu HCl will be equal to 1 into 35 divided by 1 plus 35. It is nearly equal to 1. Okay. So if you substitute these values here, so it will be equal to root of 2 by 1 equal to root 2. Okay. So it's nearly 1.4. The answer is given as 1.395. Okay. Question number 14. The boil temperature Tb is defined as temperature at which the properties of real gas coincide with those of an ideal gas in the lower pressure limit. The graph that shows the pressure dependence of the compression factor set for real gas at Tb is. Okay, let's see how to solve this question. So if you look at the standard textbooks of physical chemistry, you can see a plot like this, the relation between the pressure and compressibility factor. Okay, so the plot will be like this. Z here and 1 0. Pressure 200, 400, 600, 800 like that. Pressure in atm. So the plot will be like this. This is for helium, this is for hydrogen, this is for CH4 and this is for NH3. So this will be the nature of the plot for real gas and ideal gas. So these two, hydrogen and helium, can be considered as ideal gas. For CH4 and NH3 it will be like this. So if you look at these plots and if you look at the options, we have a confusion that it may be we may tick the question option C, but the question, if you go through the question thoroughly, there is one more additional point. That means the question is given like this: the graph between compressibility factor and pressure for real gases at TB. At TB, the nature of the plot will be like this: pressure Z. Okay, so it will be like this. At TB, the nature of the graph will be like this. So the answer is option B. This is the answer. Okay. Question number 15. The major product formed in the following reaction sequence is. This is the molecules given. So first, this is Grignard reagent. So we know Et minus is the nucleophile. It will undergo 1,2 addition. Mainly Grignard reagent undergo 1,2 addition. We have two choices here. This is known as 1,2 addition. Okay. This is known as 1,4 addition. Okay. So if you have an alpha beta unsaturated carbonyl group, we have two choices like this, but normally Grignard reagent undergoes 1,2 addition. So let's go for 1,2 addition. Okay. So if it undergo 1,2 addition, the product will be like this. So it will become OMGBr and Et will be here. Okay, ultimately we know OMGBr will become OH. So it will become OH. So I write here OH, I write here. Okay. Now what is the next reagent given? CrO3. So now we have to treat this one with CrO3. OH, Et plus CrO3. The structure of CrO3 will be like this. So it will attack here and it will move like this. So we will get the product like this: Et O Cr double bond O, double bond O, O minus. Ready? This is the product you will get, and it will undergo 3,3 sigmatropic reaction. Okay, sigmatropic reaction. Okay, we know the application of CrO3. CrO3 is an oxidizing agent. Normally it converts alcohol to aldehyde or ketone. Okay, oxidation of alcohol is the function of CrO3. But if you have this type of, this is a particular type of OH. What is the peculiarity? This is an allylic OH. If you have an allylic OH, the reaction will be like this. Okay, so it will undergo 3,3 sigmatropic reaction. So it will be like this. So the double bond will be here. Et is here. It is here. Oxygen now. Double bond O, double bond O, O minus. Okay. So it will become OH. So let's write like this. What is the next step is this one. One of the hydrogen from here, this will move like this. Okay. So ultimately we will get the product like this. Et double bond O. Okay. This is the product you will get. What is the next step is, we are treating with PH3P double bond CH2. This is known as Wittig reaction. Okay, during Wittig reaction, what happened? This will be substituted by this. So we will get the product like this. AT double bond CH2. This is the final product. So the answer will be option B, second option. Second option is the correct answer. Question number 16. The geometries of the species Br3 plus Br3 minus and Brf3 are respectively. Let's see how to solve this question. So these are the molecules given, Br3 plus. So what will be the structure? If you draw the Lewis structure of this complex, this molecule, bromine has 7 electrons around it. Okay, Br3 plus. So bromine has 7 electrons, and this bromine forms a bond with 2 other bromines. Okay, so let's draw like this, bromine and bromine. Okay, and this bromine also have 7 electrons. So this will be the structure, and there is a plus charge here for the molecule, so 1 electron will be missing. So this will be the final structure of Br3 plus. Okay, so if you look at this central atom, you can see 2 bond pair. One is this 2 bond pair plus 2 lone pair. That is the situation for this one. What about here, Br3 minus? So Br3 minus will be like this, Br, 7 electrons around it, 1 forms bond, 1 form bond. Okay, now we have 7 electrons around bromine. So now we have 2, 4, 6, 7 plus a minus charge, so additional 2 lone pairs. Okay, this will be the structure of Br3 minus. Okay, so this will be the structure of Br3 minus. So you can see it here, 3 lone pair plus 2 bond pair. That is the situation. And Bf3, what about this one? Brf3, okay, F, and bromine has 7 electrons around it, and 1 forms bond with her like this. Now remaining 2 bond. Okay, so it will be 3 bond pair plus 2 lone pair. So that is the situation. Okay, so if you look at the question, you should be careful, because there are 2 chances. The question likely to be geometry. So in this particular question, they ask about the geometry. The question also can about shape. So there is difference between geometry and shape. If you are thinking about geometry, you just think about the system like this. We have total number of pair of electrons. Here we have 4 pair of electrons. Okay, here we have 5 pair of electrons. Here we have 5 pair of electrons. Okay, so if you have 4 pair of electrons, the geometry will be tetrahedral. Geometry is tetrahedral. Okay, so whatever the number of bond pair and lone pair, that doesn't matter for geometry. Okay, the total number of pair of electrons, that is the concern for geometry. Okay, so geometry is tetrahedral here. If you have 5 pair of electron, trigonal, bipyramidal, this is also trigonal, bipyramidal. Okay, if the question is about shape, the idea will be different, so you should think differently there. Okay, so you should apply the VSEPR theory if the question is about shape. Okay, but in this particular case, it's about geometry, so this is the idea. So the answer will be tetrahedral, trigonal, bipyramidal, and trigonal, bipyramidal. The answer is option C. Question number 17. The cage type structure adopted by boron hydrate B5H11 is. Okay, let's see how to solve this. The molecule given is B5H11. So Bn HN2 minus is closed. Bn Hn plus 4 is nido. Bn Hn plus 6 is arachno. Bn Hn plus 8 is hypo. Okay, this is the concept. So we have given B5H11, so it will be Bn Hn plus, so let's write it like this, B5H5 plus 6. Okay, so Bn plus 6, that is arachno. Okay, so the molecule is arachno. The answer is option D, arachno. Question number 18. The order of MC bond strength in the following species is. Okay, let's see how to solve this. So these are the molecules given. So what happened? It's all asked about metal carbon bond strength. Okay, MC bond strength. So metal will have two types of bonding with carbon. One is like this. This is sigma bond, and another type is like this. Okay, in metal carbonyls we have two types of bond. One is sigma bond, this is sigma bond, this is sigma bond, and this is pi bond. Okay, to form a sigma bond, carbon donate electron to the metal. Okay, electron will be flowing from carbon to, so I am talking about metal carbonyls. Okay, so to form sigma bond, carbon will donate electron to the metal. To form pi bond, the metal will give electrons to the carbonyl group, so that the flow of electron from metal to carbonyl group. Okay, so in this particular case they are asked about metal carbon bond strength. Okay, so CO is a very good pi acceptor. Okay, so if the donation of metal to carbon electron density increases, the ability of metal to carbon donation increases, then the metal carbon bond strength increases. Okay, that is the idea. So if we have metal have excess electron density on metal, the electron will flow from metal to carbonyl group. So that means the strength of pi bond increases, that means metal carbon bond will become stronger. Okay, so electron density on the metal increases, metal carbon bond strength increases. That is the idea. So you can see it here, you have two minus charge here in this case, so that will have high metal carbon bond strength. So the order will be 3, then comes this one minus charge, then 4, then this one 1, then 2. So this will be the order. So the answer will be, answer for this question is option C. Question number 19. The number of non-bonding electrons present in the frontier molecular orbitals of HF is. So to solve this question, we should know the molecular orbital diagram of HF. The molecular orbital diagram of HF is like this. I am plotting the hydrogen here, the orbital of hydrogen here, HF here, and fluorine here. Okay, so the plot will be like this. This is oneness of fluorine. Oneness of fluorine has 2 electrons. The electronic configuration of fluorine is 1s2, 2s2, 2p5. This is the electronic configuration of fluorine. Okay, so actually this is 2s. Okay, so I am not plotting the 2s orbital. So 2s have 2 electrons, so it will be like this. Next we will plot the graph for 2p. So the 2p orbital will be like this. 2p orbital of fluorine, and this is the 1s orbital of hydrogen. Okay, this is the 1s orbital of hydrogen. Ready? This is 1s orbital of hydrogen, and the plot is like this. Ready? So this is the plot. We have 1 electron here, we have 5 electrons here. Total 6 electrons. So this is non-bonding because there is no hydrogen involved in this bonding. This is non-bonding. This is also non-bonding. Okay. This is sigma orbital. So this is the plot for HF. Okay. In the question paper, it is asked about the number of non-bonding electrons in HF. Actually, this is also non-bonding, but we in the questions they only consider this one. So the answer is given as 4. This is the number of electrons present in the non-bonding electrons. Okay. So the answer is option B. Question number 20. The coordination number of aluminum ion and the number of bridging hydrogen atoms in Al, BH4 4 times minus are respectively. Okay, this is the structure of the molecule. You can see it here. So the number of hydrogen bridging will be, the question is about the coordination number of aluminum ion and number of hydrogen bridging. So you can see the coordination number of aluminum is 8. 8 hydrogen is attached to aluminum. So the coordination number is 8, and the number of bridging hydrogen is also, number of hydrogen bridging is also 8. So 8 and 8 is the answer. So the answer is option A. Okay. So this is all about question number up to 20. So let's meet on the next video with question number 21 to 30. Okay. Bye.